Okay, so let's do question 5. If all is well, we can do question 5. So question 5 is saying, question 3. Question 3. So question 3 is about a Cobb-Douglas production function. Right, so we have a Cobb-Douglas production function right here, which is so the function is that's too much. Yeah, so we have a Cobb-Douglas production function which is saying Q is equal to A capital to the power alpha labor to the power alpha minus 1. Okay, then so this is what we call the objective function, right? So this is what we call the objective function. Then we have the constraint, which is the total cost is that plus that. So the first part here is the cost of labor. Okay, so that's the cost of labor, and then the second part there is the cost of capital. So in this case, yeah, so in this case we have the objective function against this total cost. Okay, then the question is saying kindly confirm, can you see my screen?
We are able to.
Okay, you can follow through like everything, even what I'm writing.
Yes.
Okay. Okay, that's fair. Okay, that's fair. All right, so where Q is the total product, so this Q that we are seeing here is the total product, and then for us to produce Q, we need two inputs, capital and labor, right? And then yesterday we said that this alpha here that we are seeing, so the alpha shows the proportion or the contribution. Okay, so alpha is the contribution. It's the contribution of capital to total output, right? So that alpha is showing us the contribution of capital to total output. Okay, so right now we're just doing the interpretation of the function. Then the alpha minus 1 shows the contribution of labor. Okay, so that's the contribution of labor to total product or total output. Okay, yes, like that. So the alpha minus 1 is the contribution of labor to total product, and then the cost that we have is this one over here, and this cost is the total cost. All right, so this is what we call the constraint. So we are constrained by this cost. Okay, so that's our constraint, and then this one here is the objective function. So that's the objective function. All right, okay, cool. Now the question is saying, using the Lagrangian model, can we use the Lagrangian model to determine the following? Okay, so A there is asking us to determine the optimum level of capital in labor quantities. Okay, now for us to use the Lagrangian function or the Lagrangian model, we first have to identify this, that we are going to define a certain function, okay, called L, and this L should equal the objective function. So we are going to put the objective function first, objective function plus there is something called lambda, okay, where this lambda is what we call the Lagrangian multiplier, okay. Then after putting the lambda, we are going to multiply this lambda by the constraint, okay. So we are going to multiply our lambda by the constraint. After putting up such a function, it will be safe to call this function the Lagrangian function, okay. So it will be safe to call such a function the Lagrangian function, okay. Now can we put this thing together now, right? Because we have the bits. So therefore L should equal our objective function, and the objective function is a k alpha L to the power alpha minus 1, okay. So that is our objective function. After putting the objective function, we should, okay, so after putting the objective function, we should then put the lambda. Then we're going to multiply this lambda by the constraint. Now remember what we said yesterday. We said that when putting the constraint, make sure that you put the c, which is the actual cost, then you get everything on the right. Remember, we are talking about this function here, we're talking about that function there. So after putting the c's, okay, we should get everything on the right to the left, okay. And we know that once we do that, everything on the right will have to change the sign when you take them to the left hand side, right? Because this side is, they are positive, but when you transpose them to the other side, these will become minus, they will become negative, okay. So it's gonna be c minus wl minus rk, like that, okay. After doing this, okay, after putting up the Lagrangian equation, so this that we've done here is a Lagrangian equation. After putting up the Lagrangian equation like this, next will be to open the brackets. So we should open these brackets there. In short, we're going to distribute this lambda throughout, okay. We're going to distribute the lambda throughout. So this L is going to equal ak alpha to the power alpha to the power alpha minus 1, and then plus. Now we're going to start multiplying lambda times c. We are going to have lambda c, all right. Then positive lambda multiplied by negative wl, we're going to get minus lambda wl, and then it's obvious that the last part will be minus lambda rk. From here, next step is to partially differentiate this function. So partially differentiate the function. So partially differentiate this function with respect to k, l, and lambda, okay. So later on I'm going to give the interpretation of lambda, like how we interpret the lambda. All right, so we are going to partially differentiate this function with respect to capital, labor, and lambda, okay. Now can we do the partials now? So I'll move this thing up so that we can have enough space. So we are going to get the partial of L with respect to, let's start with capital. Okay, so we know that with partial derivatives we are only going to pay attention to those terms containing k in this case, right? So we know that, or we can see that k is in this term and k is also there. Okay, so we're going to concentrate only on these terms there. So therefore, in the first part there, we are differentiating a Cobb-Douglas production function, okay, with respect to k. So we know that since this k here is raised to the power alpha, that alpha there will have to drop. So it's going to be alpha. We are multiplying this alpha by a k, but now we know that the power of k should drop by 1, or the power of k should reduce by 1. In short, we should remove a 1 from the power of k, just like any other differentiation, right? So that one is going to be alpha minus 1. So this is for capital, and since we are dealing with capital, labor is going to remain unaffected. Okay, so we have this here, okay, and then the last term is minus lambda r k. Now we are differentiating this term with respect to k. Okay, so we can put our minus there. So can we solve this one here? So I've got lambda r k. We know that this k is raised to the power 1. Okay, so we know that when differentiating this whole thing with respect to k, that power of k should come this side here. So it's going to be 1 multiplied by lambda. We are also multiplying this with r, and we know that we are also multiplying it with k, but now we know that from the power of k we should remove a 1. Okay, all right, so we have 1 times lambda r. We are multiplying this by k. We are multiplying that by k. Okay, and then the power of k will be 1 minus 1, and we know that 1 minus 1 is 0. So therefore this is when we are saying lambda times r, but we're multiplying this with k, but this k is raised to the power 0, and anything raised to the power 0 is a 1. Therefore we know that this will just be lambda r, right? So we are going to put our lambda r there. We equate this to 0 as usual, because remember, every time we differentiate a given function, we equate that to 0. Okay, so that is how we have that term there. So here this is just, so let's call this equation number 1. Okay, so let's call this equation number 1. So this is the partial derivative with respect to k. Next is to get the partial of our function with respect to labor. Okay, remember that with the partial derivatives you only pay attention to those terms containing that particular variable under consideration, while keeping every other variable constant. So therefore, since we are differentiating this function with respect to labor now, we know that labor is present here, and labor is also present here. Okay, here. Therefore, we are only going to pay attention to these terms that have been circled. Okay, right, so let's do that. So let's start with the first term. So the first term is a k alpha l to the power alpha minus 1. Okay, so we are differentiating this with respect to labor, and we know that labor is raised to the power alpha minus 1. Therefore, that power, the alpha minus 1, should drop, then we multiply by everything. Okay, so it's going to be alpha minus 1 remember that this alpha minus 1 is the power of labor. Okay, so alpha minus 1, we are multiplying this by a. So since we are differentiating this function with respect to labor, capital is going to remain unaffected here. Okay, so capital to the power alpha, then labor. Now remember, we are differentiating with respect to labor, and we know that after doing this, the power of labor should reduce by 1. We should remove a 1 from the power of labor, and the power of labor is alpha minus 1. So we are saying that from this power, the alpha minus 1, can we remove a 1? Okay, so I have this term, and then the last term there is, let me just admit someone. All right, the last term there is minus lambda WL. Minus lambda WL. I mean, by now I must assume that we know that when you differentiate that term with respect to L, we're just going to have minus lambda W. Okay, we equate this to 0. So let's call this equation number 2. Okay, lastly, can we get the partial of L with respect to lambda? Okay, so now let me erase the red part. All right, anyways, yeah, so we know that the parts containing lambda is just the last part. We know that, so the parts containing lambda, I'll write that here. We're going to have lambda C minus W minus lambda WL minus C lambda RK, right? So these are the components that are containing lambda. Now here's the key thing, when differentiating with respect to lambda, don't panic. Always remember that when I differentiate a given Lagrangian function with respect to lambda, the answer is in everything that is in the brackets. So remember, what is in the brackets is this. Okay, so when you differentiate this function with respect to lambda, we're just going to get back the constraint. So we're going to have that minus C, that we equate this to 0, and we're going to call this equation number 3. Okay, yeah. So far, how is it? Am I too fast, or maybe how is it? Is it okay? Let me get the feedback.
Can you please repeat on number 2, the second equation?
The second equation? I should. Okay. Let me repeat on the second equation. Okay. So the second equation, we are differentiating with respect to labor, right? We are differentiating with respect to labor. Okay. So what I'll do is this. I'll redo the work so that we are able to. Yeah. Okay, yeah, so let me just redo the work. So we are getting the partial with respect to labor. Okay, so can we do that? Okay, fine, right? So we want to get the partial of L with it's labor against labor, right? It's okay. So change in L due to change in L. I don't like this because it's on top of got L, down of got L. What can we do? Okay, let's rewrite the. It's okay anyways. But no. But yeah, we can't have change in L due to change in L. Mathematically, that is wrong. Okay. So what I'll do is, instead of putting L in the first letter, let's put, which one? We put any letter. Well, we can put any letter. Let's put E. Okay. So it's okay. It doesn't matter. Even if we put E or L, it's okay. Okay. Yeah. So we are differentiating this Lagrangian function with respect to labor. Now, remember that with partial derivatives, right? With partial derivatives, so what I'll do is I'll also rewrite this part because it's a bit messed up there. All right. So I'm going. Please let me call you back. So plus lambda c minus lambda wl minus lambda rk. Okay, good. So we want to differentiate. My assumption is that you can hear me. All right, is my assumption correct? Okay. Okay, yeah. So we want to differentiate this with respect to labor, right? Now, remember, it's just a normal, just like the way we differentiate any other function. Only that now, you know, this function we have introduced new terms, the Lagrangian, Cobb-Douglas. Otherwise, the concept is just the same. Okay, so may this language not scare us. Okay, so we know that there is labor there. Okay, there is also labor here. So we are going to differentiate with these two terms with respect to labor, right? And remember that if we have a function, right, y is equal to a x to the power n. Remember what we do to get the dy dx. Okay, we say that the power is going to come I don't know if this is front, yeah. Then we're going to multiply that by a and x. Okay, then yeah, so we're going to multiply this by a and an x. Okay, and x, and then from the power of x we are going to remove 1. Okay, so it's the same. So the logic is the same even here, right? The logic is the same even here. Okay, yeah, the logic is the same even here. So we're going to do the same thing. So remember, there we've got a k alpha l to the power alpha minus 1. We know that we are differentiating with respect to labor, and this labor is raised to the power alpha minus 1. But since capital and labor are multiplying, remember what we do when two terms are multiplying and we want to differentiate with respect to 1? We deal with that variable that we want to differentiate and keep the other guy unaffected. Okay, so in this case, the a, the k will remain unaffected. It's only labor that is going to get affected by this. Therefore, since labor is raised to the power alpha minus 1, it is this power, the alpha minus 1, we should first drop. So alpha minus 1, okay, then this alpha minus 1 is multiplying by, we're going to put back the a and the k just the way they are. So it's a k to the power alpha. Then this labor, okay, initially this labor was raised to the power alpha minus 1. We know that from the power of labor we should remove a 1, right? So it's going to be the power of alpha, so the power of labor is alpha minus 1, but from this, can we remove a 1? Then we close.
Lungu, are you writing something down?
You can't see what I'm doing, Mr. Msonda. Are you here?
I'm here.
Are you also experiencing the same problem?
What you were writing previously is still there, but I don't know if you're still writing because I thought you're just explaining as at now.
Oh. Jeez.
Shown, but they were not showing when you were writing.
Oh. Can you see my screen?
It's still in.
I didn't get that.
Not yet. It's still loading.
Oh, it's still loading.
I think so. It's not yet showing.
Okay.
Yeah, we can see it now.
You can see it now?
Yeah.
Okay.
So we are able to see up to equation 3. I think we will some after that.
You're able to see up to equation 3. Okay. So, Mr. Thompson, don't unmute yourself. I still want to have a conversation with you, just to confirm. Okay, so can you see the brackets that I've introduced?
Which one? The one in red?
No. So I can see that it's also lagging because I've also joined using my other gadget. They are showing
now. This is when they are showing now.
Okay, that's okay. So you can continue then.
All right.
Yeah, so every time I receive a complaint, I'm also joining using my other gadget so that I can see what's going on. Okay. Oh. Okay, it's okay. Let's redo this. Okay, just a second. Okay, so we were saying that we are trying to differentiate the second part, and the second part is so the first part, remember, it's partial derivatives, and we're saying that we are only, in this case, since we're differentiating with respect to labor, we are only going to pay attention to those terms where labor is featuring, right? And the first term where labor is featuring is this term here, which is A, right? So I've got A, K alpha, okay, then L to the power alpha minus 1, okay? So it's this term that we want to differentiate there with respect to labor, okay? So we know that this labor, the term labor is raised to the power alpha minus 1, and we know that mathematically, okay, so let me just do this a bit. So mathematically, if I have an equation y is equal to ax to the power n, okay, yeah, so if I have an equation y is equal to ax to the power n, and we want to differentiate this with respect to x, yeah, so we do the dy dx. We are saying that this is equal to the power there, the n is going to drop, then we're going to multiply with a and also with x, right? And then from the power of x, we're going to remove a 1, so it's going to be n minus 1, right? So the logic is the same. Even here, we're going to do the same thing. Okay, in this case we are differentiating with respect to labor, right? So we are differentiating with respect to labor, and this labor is raised to the power alpha minus 1. So it is this alpha minus 1 that is going to drop. Okay, then we're going to multiply this by a k alpha. Okay, and then the power of labor should reduce by 1. So it's going to be alpha minus 1 minus 1. So the first part there, the alpha minus 1, is the power of labor, which is the n. Okay, so remember it's n minus 1. So the power there, the n, is alpha minus 1. So from the n, can we remove a 1? Okay, so it's going to be alpha minus 1, then minus 1. And we close that. Okay, then after doing this, so meaning that the first part there, as we are differentiating, right? So the first part there, the change in E due to change in L is going to be that term there. Okay, alpha minus 1 Are you able to see what I've written? The alpha minus 1? No, right? Yeah. I don't know what's going on. Yeesh. Okay, yeah, so the change in E due to change in L is going to equal the alpha minus 1, which is the power. Okay, and then we're going to multiply this by the A K alpha, then labor alpha minus 1, then we do that minus 1, we close. So this is just the first part of in short, this is just the Cobb-Douglas function. Okay, so of course this is after differentiating the Cobb-Douglas function with respect to labor. Okay, then after doing this, we should then do the other part. Okay, and the other part is minus lambda WL. Remember, we're only following those parts that where we are only following those parts where labor is. Okay, and then the next part that is containing labor is minus lambda. So it's this part there, which is minus lambda WL. Okay, so we want to differentiate this with respect to labor, and we know that this labor is raised to the power 1, so that is going to be 1 multiplying with the multiplying with lambda, multiplying this by W, and then labor. But we know that from the power of labor we are going to remove a 1, like that, and we know anyways that this is just going to be minus lambda W. Just that, minus lambda W, because this labor is now going to be raised to the power 0. Why? Because 1 minus 1 is 0. Okay, and anything raised to the power 0 is a 1. So therefore the full derivative with respect to labor is this one here, alpha minus 1 multiplied by AK alpha, then labor to the power alpha minus 1 minus 1. Okay, then we put minus lambda L. So in short, the key here is us knowing when to apply the partial derivatives. And also we should also understand how to differentiate, how we use partial differentiation. Okay, but of course, as we're using partial differentiation, there is also one component that we should also pay attention to, and that is that we should be able to know we should be able to know the difference between differentiating terms like, let's say, 2k plus 2l partially, okay, and also differentiating a term 2kl. So the difference between these two is that in the first case there is a plus in between, okay, and since there's a plus in between, this is telling us that when I'm differentiating, for instance, with respect to capital, I'm completely going to forget about the other term. Okay, in short, the other term will have nothing to do with my final answer. But when these two terms are multiplying, like the second case there, I'll deal with k, for instance. Okay, I'll deal with k, but I should put back my l because these two are multiplying. Okay, so that is the key with partial differentiation. If in between there's a plus or minus, in that case we are only going to pay attention to that term containing that variable that we're looking for and completely forget about the other one. But if the two terms are multiplying, yes, we are going to pay attention to that term that we are looking for, but we should put back the other term. Okay, so that is a difference. So the moment we understand this simple logic there, partial differentiation will become easier to handle. Okay, all right. How is this so far? How is this so far? Is it okay?
Fine.
Okay, I'll assume that you said it's okay now. Okay, because I didn't really get that. You were a bit fast. Okay, all right.
Mr. Lunga, I forgot to put the equation 2 to 0.
Oh yes, you're right. So this is equal to 0. Okay, yeah, that is equal to 0. You're right. Okay, now, so this what we've done so far is just doing the partial derivatives. Okay, so what we've done so far is just to handle the partial derivatives. Next step is okay, yeah, so the next step is to so after you've done the partial derivatives, right, the next step there is just to simplify a bit. Okay, you just have to do some simplifications here and there to show that you're a mathematician. How? Okay, so what you can do is in the first equation, from equation 1, what can we do from this? Nothing literally, but anyways, you can just say, okay, can we open the brackets there? Okay, so we can try to open the brackets there. I can see that it's still lagging, so I'm really failing to understand if it's my internet that is weak or what. I don't know. Okay, yeah, so from equation 1, let's see what we can do there. So we can just open. Okay, so from equation 1, that can be, so that will become alpha a k alpha minus 1, then labor alpha minus 1, yes, then minus c lambda r is equal to 0. We're just opening the brackets, right? and then from equation 2, this is just going to become, so what we can do here, we can simplify the power there. So this is going to become alpha minus 1 like that. Okay, we are multiplying this by a k alpha L to the power. Now remember that the power of labor is alpha minus 1 minus 1. So it's more like we are saying alpha minus 1 minus 1. Okay, so we know that this is alpha minus 2, because minus 1 minus 1 is minus 2. Right? So therefore the power of labor is now going to become alpha minus 2. Okay, then we close this, we say minus lambda L is equal to 0. Okay, that is from equation 2. From equation 3, equation 3 is just going to be the same. Okay, so C minus WL minus RK is equal to 0. Okay, now after doing this, the next step is to
sorry, Mr. Matam.
Yes, madam.
On the second one, is it not lambda W equals 0?
Oh, you're right. You're right. It's supposed to be lambda W. You're right. Yeah, lambda W. Okay. All right. Yes. So after doing this, the next step is to say, okay. So after doing this, you deal with these the first two equations. Okay. So let me write something here. After doing this, let me say take lambda R and lambda W on the other side. Okay, on the other side. Okay, what does it mean? It means that what we can do is, we are going to say in the first equation, the one that we've differentiated with respect to capital, we are going to say lambda. Okay, I see that it's already misbehaving. Okay, so yeah, you have to take lambda and lambda R and the lambda W on the other side. Okay, so you take these two on the other side. What does that mean? Well, it means that, okay, so this means that from the first equation, the one that we've differentiated with respect to K, we're going to have alpha A K alpha minus 1. Then we've got labor alpha minus 1. Okay, we should say this is equal to lambda R. That's what I mean to say. Can we take the 2 on the other side? And then from the next equation, the one that we've differentiated with respect to labor, which is open brackets alpha minus 1 multiplied by A K alpha labor alpha minus 2. Okay, can we equate these to lambda W? In short, this is what is called the okay, I'll introduce this concept the next step. Okay, but for now, yeah, can we take these two on the other side? Okay, can we take these two on the other side? Okay, now after doing this, okay, after doing this, the next step, which is very important, okay, the next step, which is very important, we are going to like convert these into ratios. So convert the above. Convert the above into ratio, into a ratio. What does it mean? What I mean is, we are going to say that, okay, we are going to say that the first part, which is this, in short, we're just going to make a fraction on the left and make a fraction on the right. Okay, we're just going to make a fraction on the left and also make a fraction on the right. That's what I mean. So this will be alpha a k alpha minus 1 labor alpha minus 1 over, okay, alpha minus 1, okay, for the other one, open brackets, ak alpha, then labor alpha minus 2, okay, is equal to lambda r over lambda w. So this is what I mean. So let me just repeat. Okay, so remember, after doing the partials, okay, after doing the partials, we opened the brackets, which is this step here. Okay, we opened the brackets. After opening the bracket, we said, can we take lambda and can you take lambda r and lambda w on the other side? After doing that, we've said that, well, which is here now, can we convert this into a ratio? Okay, can we convert this into a ratio, which is what we've done here. So those terms with lambdas, can they make a ratio on the right? Those terms without lambdas, can they also make a ratio on the left? Okay, then what we can see is that on the right there's something common. There's a lambda on top, there's also a lambda down, meaning that this lambda on top and the lambda down can cancel. Alright? Okay, meaning that this is going to reduce to so this is going to reduce to something like this: alpha a k alpha to alpha minus 1, then we've got labor alpha minus 1 divided by alpha minus 1, then open brackets a k alpha labor alpha minus 2. We are saying that this is equal to lambda over this. Now this here is what is called the equi-marginal principle. So if you have done micro before, you should be familiar with this term, equi-marginal principle. What does the equi-marginal principle state? Well, this is telling us that at the, in this case, at the output maximizing point, the marginal productivities of capital and labor, the ratio of the marginal productivities of capital and labor should be equal to the prices of these two factors of production. So the ratio of the marginal productivities, which is on the left, is equal to the ratio of the prices of these two. Okay, so this is what we call the equi-marginal principle. So the aim of this is to reach here, because when we reach here, then work has been simplified. Okay, so the aim is to reach the equi-marginal principle. The moment we reach the equi-marginal principle, then the work has been simplified, because from here onwards we're just going to apply the laws of indices. Okay, we're just going to apply the laws of indices, and then after applying the laws of indices, then everything is simplified from that. So the hardest part is what we've done. Okay, so the hardest part is what we've done, because here now, from now onwards, we're just going to apply the laws of indices. Okay, which by assumption, I will assume that we are okay with the laws of indices. So remember, with the laws of indices, okay, so in this case we're just going to use one rule, okay, and that is the rule of division. Okay, so the rule of division. Okay, what does the rule of division state? Well, it says that if you are dividing two terms with a common base, okay, so as long as you are dividing, maintain the base. Okay, so can we maintain the base? So maintain the base and subtract the powers. Okay, so maintain the base and subtract the powers. Okay, so we are going to maintain the base and subtract the powers. Okay, now if you look at this, the ratios that the ratios that we've come up with, if you look at the left hand side, okay, there is something common on top and also something common below. Okay, let's analyze. So the top part on the left, we have got capital, and in the denominator we also have got capital. So there is something there, so the base is the same, k. Okay, so this rule is telling us that if you are dividing, because this is division, okay, so the numerator divided by the denominator, so we are dividing. If you are dividing and you have got the common base, can you maintain that common base and subtract the powers? The same applies to labor. There is labor on top, there is also labor down there. Okay, so there is labor on top, there is also labor down there. This then means that we should do the same. Now can we put this into practice? Okay, so can we do that? So this then means that the numerator will be, okay, so the numerator will be alpha. So the numerator will be alpha a. Now can we maintain our base? What is our base? Our base is capital. Okay, so our base is capital, and then the capital in the numerator is raised to the power alpha minus 1. Okay, so we are saying that can we maintain the base, and so this means that this capital, this k here, is representing the capital on top and also the capital down. Now the capital down there is raised to the power alpha. Okay, so the capital down there is raised to the power alpha. So we're going to say we're going to keep our base, the k, and then subtract the powers. So the power for capital on top is alpha minus 1 minus the alpha down for k. Okay, you see that? And then the next is to deal with it. So don't worry about this alpha minus 1 down there, we're going to put it. For now, can we deal with, yeah, the next is labor. So there is labor down, there is also labor up, so we're going to maintain our base, the labor. The labor above is raised to the power alpha minus 1, so it's alpha minus 1 for the labor above minus the power of the denominator, which is alpha minus 2. So we're saying that that is just going to be divided by alpha minus 1, because now yeah, oh yes, oh, and one more thing, right? One more thing. Have you noticed that on top we've got a and down we also have capital A? Okay, so this means that the a on top and the a down can cancel. Okay, meaning that in the denominator we are just going to remain with alpha minus 1, Why? It's because this capital, the capital down there has been dealt with already, okay? And then this labor to the power alpha minus 2 has already been dealt with already, because we've maintained the base and then we've subtracted the powers, okay? So we are saying that this is equal to R over W, okay? Next is just to, so meaning that this A shouldn't be there then, because we've already cancelled it with the A down, so the A there should disappear, okay? Meaning that there we should just have alpha, okay? Now like this we just have to do the subtraction now, okay? Should just do the subtraction there. So next is to do the subtraction. So on top we have alpha. Now with k we are going to put our k, then we're just going to subtract the powers, right? So as you can see there, the powers, we have got alpha minus 1, right? Okay, so for the powers we've got alpha minus 1. Let me try to refresh the page. Okay, yeah, so for the numerator we have got ak, and then the k is now raised to the power alpha minus 1 minus 1. So we have got alpha minus 1 minus 1. Alpha minus 1 minus alpha, minus alpha. So it's more like we are saying alpha minus 1 minus alpha. So we know that this alpha here is positive, okay, and then that alpha there is negative, meaning that these can cancel, meaning that in short the k is now only going to be raised to the power minus 1. Okay, so in short our work is becoming simplified slowly but sure, okay? And then the labor is now raised to the power alpha minus 1 minus alpha minus 2. So you know what, if you have noticed, we've just been dealing with algebra, okay? So we've just been dealing with algebra. So now the power of labor is alpha minus 1, okay, this minus alpha minus 2, okay? So this is more like we're saying alpha minus 1 negative alpha plus 2. Okay, so we are just going to distribute that negative there and do our mathematics. So this alpha and that alpha will go. Minus 1 plus 2 is just positive 1, meaning that our labor is just raised to the power 1 there. Then we are dividing this by, by alpha minus 1, then this is equal to R over W, like that. So as you can see, we are almost there now. Okay, yeah, then from here, we're just going to cross multiply and forget about this, okay? So from here the next step is to should we start with cross multiplication? I'm trying by all means to find the easiest way, okay, so what we can do is, let's just do the cross multiplication. So from here, can we do the cross multiplication? Okay, so can we do the cross multiplication like that? Okay, so now that with cross multiplication, the alpha minus 1 is going to multiply by R, cross multiplication, right? Then the W is going to multiply with the alpha k to the power minus 1 labor to the power 1. Now, okay, so this will be, let's start with W multiplying by everything. So this is going to be W multiplied by alpha capital minus 1 then labor. This is equal to alpha minus 1 multiplied by R. Okay, right. So from here, can we make okay, one more thing. I'm sure by now we know that this k to the power minus 1 is the same thing as saying 1 over k, right? Yeah, these are just indices, right? So this k to the power minus 1 is the same thing as saying 1 over k. Okay, so I'm talking about that term there. Okay, so this therefore is the same thing as saying w alpha L over k, right, is equal to alpha minus 1 times R. Okay, it's the same thing. It's the same thing. Okay, so what we can do then is just to multiply this k by the term this side. One more thing, right? This might sound a bit, yeah, but we just have to know this. We just have to know this. We know the steps. We practice, because I mean, we will be shocked that we find this in the exam. Okay, so let's not give up. Let's try to persevere. I mean, we're almost there. We're almost reaching the conclusion. Okay, yeah, so yeah, we know that k to the power minus 1 is equal to 1 over k, which is what we've done right here. Okay, now I'm saying that, well, what we can do is, since on the left of a fraction, we can also make the right as a fraction by dividing it by 1, so that we can again cross multiply. Okay, so we can cross multiply there. We can cross multiply there. Okay, so in short, after doing the cross multiplication, this will be alpha WL is equal to alpha minus 1 times RK. So now we are done. Okay, because we can just, so from here, let's make L the subject. Okay, so let's make L the subject. Okay, can we make L the subject? How can we make L the subject? By dividing throughout by alpha W, like that, so that the alpha W on top and the alpha W down can cancel. Therefore, the optimum amount of labor is alpha minus 1 times RK divided by alpha W. So this is the value of L. Okay, so that is the value of L. So now at least we have the value of one variable. So listen to this. This has, sounded a bit complicated, a bit confusing, because we are dealing with letters. As you can see, we've not done done anything with numbers. But the moment we understand letters, believe it or not, it will be very much easier for you to handle numbers. Okay, so after this one, we are going to do a Lagrangian function with numbers. Okay, but yeah, when you're doing this with numbers, I'm telling you, this thing is easy, very much easier. But it's good that we've handled letters first, because after understanding the letters, it will be easier for us to handle the actual figures. Okay, so yeah, now we have the units of labor that we can produce, that we can produce. So if you have got numbers, don't worry, the alpha will be a number, the R will be a number, the K will be a number, the W will be a number, meaning that this L, if we're dealing with numbers, it would have been an actual number, let's say 2, 300 or whatever. But now this is just, you know, such a complicated thing. Okay, so this is what you are expected to find in that test. Okay, so my assumption is that we managed to find this. Okay. How is it this far? I know it's yeah, but let me just get the feedback.
You should ask the ones that wrote the test.
Why didn't you write the test? Yeah, okay. Mr. Peewee, are you here?
I'm here, but I'm just surprised. What I was doing in that test is just parallel to what I'm seeing.
Oh Lord. Oh yeah. Anyways, yeah, but then yeah, I mean, we're expected to do something of this nature at the end of the day. Right, yeah. But don't worry, when we do the actual numbers, you're going to see that this work is easier. Very easy. Very easy. Okay, so the only thing that you're supposed to know now is, okay, so first thing first is to put up a Lagrangian function. After putting up a Lagrangian function, we know that when putting up that function, we start with the objective function. After putting the objective function, I'm not writing anything, I'm just talking. After putting the objective function, we say plus lambda. Okay, plus lambda, then you open the brackets. In there, you put the constraint. You close. You open those brackets. After opening the brackets, you find the partial derivatives with respect to capital, labor, and lambda itself. After that, you do those gymnastics now. You take this, you take those with lambdas on the other side. You cancel the lambdas. Okay? After canceling the lambdas, you convert that into ratios. The left hand side should have a ratio. The right hand side should have a ratio, so that you reach the equimarginal principle. Okay? After reaching the equimarginal principle, then now you do those gymnastics where you introduce the laws of indices. You see that? You introduce the laws of indices, which one should go on top, which one should come down. You know, if the bases are the same, you maintain the base, you subtract the powers, you simplify that. You see that? After simplifying, then you make one of the two the subject of the formula. And in this case, we have decided to make lambda the subject of the formula. You see that? So the more you do, anyway, practically this course is like mathematics, right? It's a bit stingy, where you have to be doing these things almost every day. So at least before you sleep, you solve one question in managerial economics. Don't solve those that are theory in nature. Solve those that are mathematical in nature. Okay, you solve one before sleeping. Solve another one. Solve another one. Believe you me, by the time you sit for that exam, you'll be able to know most of the things, 90% of their work. Yeah, so that is my advice. I know that this is 20 past 9. So let's finish the work tomorrow. Okay, so at least we found one. So but question A is not even done. We've only found one. But to reduce the ambiguity, yeah, between now and tomorrow, let's try to go through the recording. We understand the concept, because tomorrow we're going to start from here and say that since yesterday we managed to get L, then can we find the capital? You see that, right? Yeah, so to reduce the ambiguity, I suggest we